And for me, it is quite difficult to talk here about quantum information because I'm supposing to replace Luis Davidovich. And Luis Davidovich was my teacher, and he is quite good in a very high level. So it's almost impossible to replace him. So I hope that I will try my best, but I hope that you give me some discounts. I change a little bit the title. I will talk about quantum information in general, but I will also talk about this quantum thermodynamics, which is a hot topic also associated to this quantum information. I'm from this university here, Federal University of ABC. This university is located in São Paulo metropolitan area, in the ABC area. The name is quite funny, but this ABC means 3 cities in the São Paulo metropolitan area: Santo André, São Bernardo, and São Caetano. So this is about 50 minutes from here by metro and train. And also, we are part of this national initiative of science and technology in quantum information. And we have a group there with 6 faculty members. This is a bit old. Here we have just 5 members, and then you hire a new guy doing some theoretical research and also experimental research in some platforms. We are interested in several topics associated to quantum information, which ranging from quantum information science in general, quantum thermodynamics, test of principles in quantum information science. We also study entanglement and non-locality, open quantum systems, quantum computation, quantum coherence aspects in general, and also in biology, and quantum metrology. These are the systems that we have available to play a little bit with quantum information in the lab. We have some nuclear qubits, quantum bits, that we can encode in molecules, in liquid state samples, and we can manipulate these spin qubits using nuclear magnetic resonance system. We can also play with some photonic qubits. We have a twin photon source working there, and we also have a squeezed light source. Then we can do some metrology using this kind of thing, and using twin photons, we can play with quantum correlations and also some tests, also in quantum metrology, but in quantum communication, etc. And now we have ion trap being constructed at UFABC, and this will be the first ion trap in Brazil. And this is the first twin photons source in São Paulo. We have twin photons in Brazil, but in São Paulo, this is the first source. And quantum information is a quite vast topic that involves a series of different sub-areas or subtopics. It is also related to what we are calling as quantum technology. I hope to clarify what is quantum technology in a few slides. And here we have a possibility to use this quantum technology to play with what we call quantum information. So the idea is to encode information in a quantum system instead of encoding information in a classical system. And then we have several different aspects of the information theory when we go to the quantum world. And we can also use this to perform very precise metrology. I don't know if you are aware about the LIGO and the measurement of gravitational waves. And then at the LIGO, they use quantum metrology to increase the precision of the measurements. And we can also use this to simulate other quantum systems. Actually, this is one of the short-time applications for quantum computation and quantum technology, and also quantum computation, of course. And we also have quantum communication. We can prepare cryptographic codes using quantum systems. And more recently, we have this quantum artificial intelligence. This is a kind of very hyped topic, and there are a lot of discussions about what is this, what is quantum in artificial intelligence. And in the background of all of these possibilities of the use of quantum technology, there is this quantum thermodynamics. So we know that the thermodynamics introduced limits for a lot of different technologies, and it's not different here. But in order to understand what are the limits of this quantum technology or the quantum computation, the thermodynamic limits of this kind of thing, we have to understand how to describe thermodynamics in a scenario where we are far from the equilibrium, where we are far from the thermodynamic limit. We have just few particles, or we have a system which has less than the number of Avogadro number of particles. So, and people start to translate and adapt the ideas about stochastic thermodynamics to quantum systems. And this area are now called as quantum thermodynamics. And this area is associated to, if you want to understand the limits, the thermodynamic limits of that system, maybe this construction of this application of thermodynamics in a small out of equilibrium system will give us some hints about these limits. I will talk more about this. So it's almost impossible to cover all these possibilities in 3 lectures. So I chose to talk about quantum computation, a little bit about quantum computation, and to give you some taste about where come from this quantum advantage, and how is the scenario for quantum computation nowadays. We have quantum computers now, very noisy computers, but we have some prototypes. Actually, we have some computers, quantum computers used in a commercial way. So this is a commercial technology. Quantum communication is also commercial technology now. Quantum metrology is also commercial. And we have some companies building some sensors and apparatus based in quantum metrology. So we will talk a little bit about quantum computation, quantum metrology, also quantum communication very fast. And then I will talk about this quantum thermodynamics, and I will show some experiments that we performed in Brazil associated to this area. So I hope that we will enjoy this selection of teams in the area that I did. I don't know how familiar are you with this topic, quantum information and quantum computation, so I prepared something very basic for today, and then tomorrow I will start to increase the sophistication of ideas and the topics. So we would say that this is a kind of this is the product of what we call the first quantum revolution. Quantum mechanics allows us to create several different devices like a transistor, and this operates using quantum mechanics. We use tunneling and also many body physics effects in order to produce a transistor. But the information that we manipulate using a transistor in a computer is classical information, is current yes or current not. It is yes or no in the logical variables, 0 or 1. And we also use semiconductors to produce light-emitting diodes and sensors for cameras. And probably this audience is quite familiar with atomic clocks, which has a lot of applications, lasers. But here we are using quantum mechanics to produce something which is useful, for example, coherent light, but we are not using quantum properties of this light. For example, when you use a laser to cut some material, we are not using quantum properties of that laser to enrich the task, to get some advantage in the task. So the second quantum revolution, the idea now is to use quantum aspects of the system to get some advantage over a classical protocol. It's not very clear in all the applications, but it is quite clear in computation. So all the computation that this computer do in the most fundamental level, in the low level of the processor, is associated to connections between logic gates. These logic gates are implemented by a sequence of transistors that can be connected in a programmable way. So here we have a truth table for operation of some logic gates. And here we have a logic gate for 1 bit. So 1 bit of information is 0 or 1. Could be in a state 0 or in the state 1. And it is associated to the presence of a current or not current, electric current. So combining these operations, we can perform any complex operation. Actually, here there are also 3 bits logic gates. So we are using quantum mechanics in order to implement the logic gates because we are using transistors, but the information is classical. So we have a lot of evolution in this kind of technology. For example, if you think about the first computers that work with vacuum valves, in a few years we got the first transistor, and in 4 years we evolved from the first transistor to a transistor which is sensible to the charge of just 1 electron. We don't have this in a commercial application, we just have this in the labs. It would be quite expensive to have this in a commercial application, maybe in quantum computation in the future. But this is what we call first quantum revolution, this microelectronics revolution. And how it is connected to thermodynamics, because I told you that the thermodynamics introduces limits for technology. For information technology, Hoflandauer, that worked at IBM in the 16, discovered what became known as the Landauer principle, that to erase 1 bit of information, the minimal energy necessary that will be dissipated to erase 1 bit of information is equal to kBT ln of 2. Kb is the Boltzmann constant, T is the temperature of your circuit, and ln of 2 because it is 1 bit. So if you look for the amount of energy that we dissipate to change the state of random memory in a conventional computer, and these data are from the commercial memories, we see that the industry is decreasing a lot this amount of dissipated energy per bit erased. So nowadays, we have something like 1,000 or 10,000 above the limit of Landauer. Here we are measuring energy in kBT. If you consider...
The paper is from 2002.
Yes, and the data are 2015. I'll talk about this. You can ask questions at any moment, please. Yes, erase a bit. Sorry? What does this mean? Let us suppose that we have a memory. You don't know what is the state of your memory, right? So your memory, you have 1 bit of memory. Your memory could be in the state 0, or it could be in the state 1, right? And then you can, whatever is the state of the memory, you want to bring it to a state that we can call a blank state. Let us say 0 is the blank state, for example. But anyway, Landauer realized that this is an irreversible process, because after the erasing, you cannot recover what you have before, right? A full erasing, not the erasing that our computer do usually, which is just to erase the table of allocation.
Yeah, it's because it's weird because if we have 0, we will always have or 0 or 1.
Yeah.
How can we erase 1, 0 or 1? Can you understand that?
Yeah. For example, let us suppose that we have a solid state memory. So we have a magnetic system with some magnetization. In order to erase the memory, you have to change the magnetization of the system. When you do it, you will dissipate some energy. But here is not about this solid state memory. This is about the random memory that we have in these computers, which are these flip-flop circuits with transistors. So if you want to change the state of your memory, you will dissipate in 95, we will dissipate this amount of energy. What the industry did was reduce the number of charges that mean 0, the difference between 0 and 1. They decreased this number. Nowadays, the number of electrons that characterize the difference between 0 and 1 is about 10 to 6 or 10 to 7. And this is a paper from a computer science magazine, and the industry has all the devices that the industry will launch in the next few years, they already have in the lab. So that's why they did this kind of prediction. Okay, but nowadays we are really between 1,000 and 10,000 kBT per erased bit. And if you back to the classical model of computation, we see the following. This is our model. This does not depend on the technology that you use to implement your transistor or to implement your logic gate. This is a kind of irreversible operation because we have more than 1 bit in the input, and we have just 1 bit in the output. For example, let us look for this logical operation, the exclusive OR. If you look for the result of the truth table, we can see that when I have a current here, I cannot say what produced this current here, if it was this configuration or if it was this configuration, right? So it's reversible. And then we believe there is no proof about this. Actually, there are some proofs with ab initio calculation of the Landauer principle, but it's necessary to assume something about the environment, about how the system interacts with the environment. So there are a lot of discussion about if Landauer is in fact the limit. But we believe that the Landauer is the limit. Actually, the major part of the community believe. Then the limit for the energy that we dissipate per logical operation in this classical computer is also Landauer. So we have this limit for erasing a bit, as when we process information, we erase bits, because the process is irreversible, is logically irreversible. If it's logically irreversible, it's also irreversible from the physical point of view, because information needs some physical system to be processed, to be stored. So this was the nice conclusion of Landauer. And then, if the industry goes in the same way, in 2035 we'll reach the Landauer limit. Probably this curve will not fit this trend, right? Probably to reach here, probably we'll need to use a single electron transistor. So this is the quite famous Moore law. Who is familiar with the Moore laws? Could raise your hands. Okay, the major part of you seems to be familiar with the Moore law. So the Moore law is in the end. Gordon Moore was one of the founders of this of the Intel company, and he realizes that about 2 years, the capacity or the number of transistors or the performance of the processors doubles. And then when we analyze the Moore laws, considering since 1978, so this is a comparison of the performance of a single core of a modern processor with the performance of the VAX computer. This is the VAX computer. So people in computer science like to do this kind of comparison of performance. And this performance is quantified considering problems like matrix multiplications and the other calculations. So at some point, the slope of this curve decreased. And now it's decreasing even more. So we are in the limit of the technology, of the silicon technology. So the size of the transistor in the silicon chips is reaching the limit of 10 nanometers, there are some mobile phones with 7 nanometer transistors in the chip. And if we build a chip smaller than this, we will start to have quantum interference between the electrons that are in one transistor and the nearby transistor. So, and also the velocity for the mobility of the electron in the material is also in the limit. And this will be a bottleneck for the internet. All of us like to see streaming videos and series on the internet. And the traffic of data in the internet is increasing a lot along the years. And that's okay, we can do optical communications, we can put a lot of information in an optical fiber, etc. But at some point, we have to introduce a router, and the router is an electronic router. We can try to do a photonic router, for example, but this will be one escape of this bottleneck. But our routers will be limited at some point. The data traffic in the internet will face this kind of bottleneck, because up to now, as we increase the number of data in the internet, we increase the capacity of our processors. So I like very much to talk about this kind of codes when I talk about quantum information. Probably some of you already saw this code, and also Luis Davidovich also liked this code. So I'm quoting Luis Davidovich in this slide, right? And Schrödinger in 1952 wrote in this philosophy journal that we never realize experiments with a single electron or an atom or a small molecule. In total experiments, one assumes that sometimes this is possible. Invariably, this leads to ridiculous consequences. One may say that one does not realize experiments with single particles more than one raises ichthyosaurus in the zoo. So this is a picture of an ichthyosaurus that I find in the Google. And we are near to raise ichthyosaurus, at least in the labs, right? Gene addition. And here are the Nobel Prizes of 2012 associated to the techniques that David Wineland developed to trap ions, and also the techniques that the Serra group developed to trap single photons and to let them interact with single atoms. So now we can, in fact, perform experiments with a single quantum, with a single degree of freedom of a quantum system. So the idea of the quantum computation is to, instead of encode information in a classical current, we will encode information in a quantum system. And let us suppose that we have a two-level system with two distinguishable states. So I have two states that I can measure. This could be polarization of light, horizontal and vertical polarization, or circular left and circular right polarization, or two electronic levels of an atom, or two states of a spin 1/2 system, anyway. And then this quantum bit, this two-level system, could be placed in a superposition state. And we don't have this possibility for the classical information. Using this possibility plus superposition, interference, and entanglement, and non-classical correlations, we can get some quantum advantage. I will try to give you some taste. This circuit is in fact the phase estimation circuit. This is what we call a quantum circuit. I will explain to you what means these symbols here. And also the initial ideas of Feynman about quantum computation was to use it to simulate other quantum systems. As the Hilbert space grows exponentially, for any classical computer will be really difficult to simulate a quantum system. And then if you have another quantum system where the Hilbert space will also increase exponentially, it will be much easier to, for example, I can use a spin 1/2 system with a lot of spin 1/2 system interacting to mimic some solid state Hamiltonian, some solid state model. Also, we can also use cold atoms to do it, and probably some lecture probably talk about it before. And this was published in this journal, The Economist. Actually, it was the cover of this journal 2 years ago. There was a series of articles about quantum technology. And this is the map of the investment in the area that this consulting company, McKinsey, did. And Brazil appeared here, very small. Nowadays, probably we will appear with a negative sign due to our government, but that's okay, we're still working. And here we have this National Institute for Science and Technology of Quantum Information with a lot of people working on that. And this point here is due to this institute. Actually, this is a kind of a delocalized institute that connects different laboratories and different groups. And each country chooses different areas to invest. And here are the investment in quantum computing, quantum cryptography, quantum sensors. There are a lot of investment in quantum sensors in Europe, also quantum communication. In US, due to the companies like IBM and the other companies, there are a huge investment in quantum information, and these are the patents and in quantum communication. But so this decreasing of the number of patents by the US does not mean that they stop to work on that. Maybe they are not communicating the results, because there are a lot of military investment here as well. So, and quite recently, so I'm now trying to influence our president. We have to show to the Brazilian president this, because he likes a lot the US president. And the US approved in the beginning of this year what they called as National Quantum Initiative. And this allows with a huge investment also in quantum technology. In Europe, there is also a lot of flagships in this area, and also in other countries. Australia has also some investment, a lot of investment, in fact. This slide was borrowed from IBM. So this is the vision of IBM about the future of computation. So the IBM thinks that in 2025 we will have quantum computation selling in a commercial way. So the model of the IBM is to sell in quantum computation in the cloud. So you can pay to access the IBM quantum computer. So the IBM quantum computer is based in a superconducting circuit, which is cooled by a helium refrigerator. So the processor operates at 10 millikelvin, about 7 millikelvin. And you can access this IBM system on the internet, and you can program an experiment. And after some time, they send to you via email the data of your experiment. So you can run a quantum algorithm in this system in the cloud. So, and they provide what they call a composer. So these squares here are unitary operations, and these lines here means that you make this two-level system interact with this other two-level system. In the architecture of this system, what plays the role of a qubit is an artificial atom, is a superconducting ring, is quit, and they get two states of this squid. It's not a flux or charge, it's a transmon qubit. I will not enter in details, but the idea is to use these two states of a superconducting current to represent 0 and 1, and then you can also couple the near neighbor rings by transmission line using some capacitive coupling. So we just need to write the Lagrangian of the circuit, then you quantize the Lagrangian of the system, and then you end up with a Hamiltonian, which is analogous to the Hamiltonian for the interaction between radiation and matter. So, and these are some companies that are investing in quantum computation, that are building quantum computation. So you have this universal quantum computation. So universal means that we can program any problem in this computer. There is also this not universal quantum computer. So this only solves one problem. So you have to map the problem that you want to solve to what the computer is able to solve. So there is this company in Canada named D-Wave that perform what we call quantum annealing or adiabatic quantum computation, and they can solve some optimization problems, but there are a lot of discussion if it's quantum or not, and the thermodynamic limit in this kind of architecture is quite severe. But they can solve some instances of very difficult computational problems. But it was not able, no one was able to show that a quantum computer that we have now, this very noisy, these computers are very noisy, there are a lot of cohering, the coherence, etc. I will talk about this. No one was able to show that this kind of computer are able to solve a non-polynomial problem. So I will talk about this in a few slides. So Google has also built, Google buy this D-Wave computer, but they also build a computer in collaboration with University of California at Santa Barbara. And IBM also has a computer with 50 qubits. Google has a computer, has different chips with different number of quantum bits. And one of them has 72 quantum bits. Also, Intel is also working on this. And several universities are also building quantum computers based on ion trap, for example. Also, there are some universities also working in superconducting. And here is what we have in Brazil. Okay, we don't have a large scale quantum computer here, but we have a few qubits processor that enable us to do some proof of principles and some tests of some aspect of quantum information. And probably some of you already saw it in some of these journals. And China put in orbit some time ago a satellite dedicated to quantum communication, and they demonstrated that it's possible to perform a video call between China and Austria using quantum key distribution, right? So they are also building optical fiber network between Beijing and Shanghai to perform quantum cryptography. And also another example of this commercial first quantum technology devices is this quantum magnetometer produced by the Lockheed Martin company. So they use NV centers in diamonds to measure very precisely at room temperature small variations of the Earth magnetic field. So the idea is to use this guy to help navigation, like the birds do. And if you have any problem with the GPS signal, you can use this kind of magnetometer to navigate. Actually, this is a device that Lockheed Martin is also selling. So let's back to computation. To talk about what a quantum computer can do or cannot do, we have to consider what is difficult or what is easy to compute. If you want to add two numbers, it's the easiest task, and this task requires a kind of something like any elementary operations if n is the number of digits. For example, when you perform an addition in your calculator, the number of logical operations grows linearly with the size of the number. When you perform multiplication, the cost of this operation is about n square elementary operations. So that's why you can multiply numbers, big numbers, very fast in a computer. But if you try to factoring a number, I will promise you that this number is the product of two prime numbers. Maybe not. This is a random number that I write, right? I did not hit with much concerning. The cost of the most efficient algorithm that you know work in this classical computer, in this conventional computer, grows like this. And this is not exponential, but this is a super polynomial. N is the number of digits of the number that we want to factorize. This is a super polynomial cost. In computation, we say that everything that costs, every algorithm where the cost grows more fast than a polynomial is a non-efficient algorithm. So at some point, you have a number that will be impossible to factoring with our computers in the age of the universe. So actually, the classical cryptography, the most knowledge classical cryptography algorithm is based in this problem, in that difficult. So there are some problems. This problem is not proved that everyone considers that this is a very difficult problem, but this problem is not proved as a non-polynomial problem in computer science. So there are other problems in computer science that there is a proof showing that the problem cannot be solved in a polynomial time with the size of the input. For example, the traveling salesman is known as a non-polynomial problem. The three satisfiability logical clauses is also a non-polynomial problem. And these problems, actually, some instances of this problem can be solved in a quantum computer, but this problem was not solved in a quantum computer yet. Actually, we don't know an algorithm to solve this kind of problem.
Sorry. You said that factoring an empty number is not an empty problem?
We don't know. There is no proof about this. Some people believe that this is an NP problem, but We don't know.
But for sure it's not a P problem. Right?
Yeah, we show that. We know that the best algorithm that we have in hands for the classical computer grows like this. Maybe someone can find another algorithm. As there is no proof that this is an NP problem, someone could find an algorithm to solve. Actually, there is also a discussion about if P is equal to NP or not. So there are people in computational complexity that dedicate life to try to prove this kind of thing. And yeah, the point is, this is a difficult problem, but we don't know if it's a non-polynomial problem. So we cannot say that the quantum computer will solve a non-polynomial problem yet. Maybe we'll be able to say it in the future. There is also problems that a computer cannot solve, like the halting problem. It's impossible to make an algorithm to test if your program will enter in an infinite loop, for example. Your test program will also enter in an infinite loop. So these are not computable problem. And probably quantum computers will not solve not computable problems. So, why factorization is important? There is this RSA algorithm for distribution of a public keys in cryptography. Actually, the major part of the banks and the major part of these systems that we use to pay something at the bar with our bank card use this kind of cryptography. So there is this public key which is distributed. Anyone can see this information, and the public key is the product of two prime numbers. One of the prime numbers is chosen in a random way. At each period of time, this could be half an hour, 20 minutes, you can decide. And then the other prime number is with the partner of the communication. So if an eavesdropper tries to listen what will be communicated, the eavesdropper will need to perform factoring in order to decrypt the code, right? And the two partners has the two prime numbers because this key is also distributed. So you have in your hands, let us suppose, you have in your hands P2, and then P1 will be randomly chosen, and then you receive this number. As you have P2, you can just divide this to P2 to get P1, and then you can perform the inverse mathematical operations in order to decrypt the information that you want to decrypt. So, as factoring grows more faster than a polynomial, we always can choose a key which is big enough to warranty security. That's why we call about 1024 bits cryptography or 2048 bits cryptography and so on. Okay, you can increase the performance of your computer, and then you increase the size of the key, and this warrant some security level. There are also other things that we can do to increase the security level. There is also another point, I have to say. As one of the prime numbers is chosen in a random way, you need to have a very nice random number generator, because if your random number generator, actually, all the random numbers that we generate in these computers are not random. They are deterministic. We just have pseudo-random number generators in classical computers. And if the eavesdropper got any correlation between the random numbers that you are generating in order to generate the key, Davis-Dorper can do a better cryptoanalysis and they can break the code. So random number generators is another application for quantum technologies, real random number generators. Because in quantum mechanics, we can generate true randomness. We can prepare a state like this. And then I can measure in the sigma z basis, 0 or 1 with 50% of probability, then I have a random bit generator, right? If my detector is good, if my state preparation is really good, is also good, I can generate random numbers in a way much more, much better than what we can do in a classical computer. Actually, this was one of the first quantum devices that was selling this quantum number generator. So let's back to our quantum bit. So we can write a general superposition of a two-level system in this way here. And we have these two angles, theta and phi. And then we can represent a two-level system in the real space, in the three-dimensional real space. So we can write a vector here in a way that the component of these vectors, of this vector that we'll call as a block vector, this is the block sphere representation of a two-level system. And the component of this vector is the expected value of the Pauli matrix, sigma x, sigma y, sigma z. And then each point of this sphere has a unique correspondence to a two-level system. This is very nice to do to visualize rotations, for example, or the dynamics of a two-level system. So, and here we can also compare what we have in quantum information and what we have in classical information. So when we have a classical bit, we only have just 2 points here, 0 or 1 in the sigma z direction. So we always use the sigma z basis to represent qubits. We call it as a computational basis. So when you read some article, we will see this reference to the computational basis. So these are eigenstates of the sigma z, right? And then a quantum bit could be placed in a superposition in any point of this sphere. For example, in the z-axis, we have the eigenstates of sigma z. In the x-axis, we have the eigenstates of the sigma x. And here we have a sphere for pure states, for states that we can write as a vector state. We have this sphere with the size of this sphere is 1. The norm of the vector is 1. So let's back to the logic gates. Okay, I can encode this two-level system in several different setups. And in a given setup, I need to be able to perform operations in order to perform computation. So one operation that we can perform is an operation over 1 bit. And in the classical computer model, the operation of 1 bit is the NOT operation. There is only one operation. And when we apply the NOT operation to the bit 0, we obtain bit 1. When apply the NOT operation to the bit 1, we obtain the bit 0. And we obtain the orthogonal state of the logical variable. Then for a quantum bit, there is no kind of operation. There is no rotation. If you don't know what is the state of your bit, if you have a generic superposition like this, if your state psi is something like this, alpha 0 plus beta 1, there is no unitary operation. In this case, it is a rotation that applied to the state psi for any value of alpha and beta. Okay, alpha and beta are complex numbers. will give you an orthogonal state, such that the internal product will be 0. If you don't know what is the state psi, there is no unitary that works for any state, right? If you know what is your state, you can produce this kind of unitary. Actually, it is easy. For example, if your state is, for example, in the hemisphere of the Bloch sphere, let us say it is a combination of an eigenstate of sigma x and sigma y, you can perform a rotation of pi over 2 of pi, sorry, in the sigma z direction, and then you will obtain the orthogonal state. But this will only work in the hemisphere of the Bloch sphere. It will not work for other states. So there is no not operation in quantum computation. But we can perform rotations. We can perform different rotations. So we can perform an operation that we call as x, which is just the application of the sigma x. We can perform an operation that we call Hadamard, which is also a kind of rotation, which is the application of this unitary. Always when I represent a matrix, I'm considering this basis, this computational basis. So the basis that I'm considering here is the basis of the eigenstates of sigma z, like this, right? So, and then we can visualize what is the effect of these operations in the Bloch sphere. And in a quantum circuit language, which is inspired in these logic gates of the digital electronics, we have the following. We will represent a qubit, a quantum bit, by a line. The time goes from left to right. And this square represents a unitary operation acting on the qubit. So just to refresh your memories, probably many of you or all of you know about rotations in the of two-level system in the SU2 group. So the generator of rotations are the Pauli metrics in this space of the two-level system, and we can write a general rotation in this direction n as this operator here. And there are many identities that we can use. This kind of identity, for example, x is just the sigma x operation. So when we put this between two Hadamard operations, we get the z operation. So it's quite useful also to implement experiments. And one difference between classical and quantum information is this one, for example. The linearity of quantum mechanics prevents us to copy quantum information. It's not possible to copy a quantum memory. This is one very easy proof of this kind of thing. Let us suppose that I want to copy the state psi. And here I have a blank state of my copy machine. And I can design a unitary that do this kind of thing. That's okay. I can also show to you which unitary do it. Okay, but if I have a kind of a universal copy machine, this copy machine should be able also to copy another state. Let us say phi. Phi could be orthogonal to psi. And then I have to design a unitary that satisfies these two equations. It's possible. In the next slide, I will show which unitary satisfy this kind of thing. But in the quantum system, I also could have this situation where we have a superposition between psi and phi. And then if we apply this unitary here that work for a single state, this will generate an entangled state. And this state is not the copy. The copy should be something like this, the copy of the superposition, right? So this is what we call non-cloning theorem. And this theorem is also important for quantum communication, for security in quantum communication. This is really simple. So if you want to copy a quantum memory, I have to perform quantum state tomography. I have to full characterize the quantum state. And quantum state tomography has a cost which is exponential. So if in the number of qubits, in the size of your Hilbert space, as you grow your Hilbert space, the number of measurements that you need to perform in order to reconstruct the state of the system increases in an exponential way. So this is what we call as 2-qubit operations. So we represent this operation like this. This will involve an interaction between this qubit with this qubit. This circle here represents what we call a quantum bit, and this is the target bit. So this represents this kind of unitary. We have a projector of the quantum bit 0. We do nothing in the target bit. If the quantum bit is 1, we will flip the target bit. The sigma x perform a flip. So this is the matrix representation, and this is what we call computational basis. We always order in quantum computation the basis in this way. When we introduce more qubits, we're still ordering in the same reasoning. So this is an example. So I told you that I will show a unitary that perform the operations that I described in the previous slide, and the CNOT gate is the unitary that performs such operations. When we have a superposition state in the control bit, we produce this state, which is an entangled state. I will talk about an entanglement tomorrow. And there are also several identities about these descriptions of these 2-qubit gates. So when we put Hadamard gates here, we can change the control and the target. We use this a lot in the lab, because sometimes it's difficult to change what is the target, what is the control. But with local rotations, we can do it. And here is what we call as a swap gate. So the state which is here will appear here, and the state which is here will appear there. So this is a swap. We are changing the state of the qubits. We can do it with 3 CNOT gates. So and here is another kind of swap. And then we can also implement a CNOT gate doing a kind of a controlled phase gate. It appears in a series of systems where you have non-resonant interaction. We can perform controlled phases. So this gate with Z is something like this. So the idea is, instead of have a controlled sigma X, you have a controlled Z. So the matrix representation is like this. In the computational basis. So if you are able to do it in your system, you are able to do quantum computation. And any operation involving more qubits can be decomposed in these 2-qubit operations plus some 1-qubit operation. So this is universal. We can implement any algorithm using this set of operations. And what is also nice about this circuit way to describe a quantum evolution, so what I'm describing here I have 3 two-level systems in these lines. These systems will interact in this way. I have this system interacting with this one. The first one will interact with the third one, and then the second one will interact with the first one again. And here we have just a control over one of these systems. And I can describe an experiment that can be performed in any setup. If I know how to perform CNOT gates and the 1-bit gate in a trapped ion, or in a optical lattice, or in a superconducting circuit, I can describe the same this protocol using this kind of algorithm, and I can apply this protocol in any system. So now we have the tools to understand a very simple algorithm, to understand from where comes from this kind of quantum advantage that I told you before. So this is one of the first quantum algorithms that appeared in the literature. This was introduced by David Deutsch in 1985. And this is known as the Deutsche algorithm, and this solves the following problem. In computation, people like a lot this idea of oracle. Let us suppose that I have an oracle, and this oracle charge me 10 reais for each question that I do. And this oracle will compute the value of a function. And this function has in his domain and image just 1 qubit. So I have some possibilities for this function. The function of the qubit x, so I will give x to the oracle, and the oracle will give me f of x. The f of x could be equal, for example, to x, or, could be equal to 0, or f of x could be equal to 1, or f of x could be equal to x, or equal to not x. This is the symbol for the not operation over 1 qubit. If f of x is equal to 0, I can choose x equal to 0 or equal to 1. We always have x equal to 0, so the function is constant, also in this case. And here we have what we call a balanced function. If I have f of 0, I will get 0. If I have f of 1, I will get 1. And here we get the not. So if I want to discover if the function that the oracle is computing is in this class constant function, or if it is in this class of balanced function, I have to question the oracle at least 2 times. If I ask the oracle just 1 time, I cannot say nothing if we are in this class or in this class. So I have to pay 20 reais to the oracle, right? So this is the cost of this task. So the task is to discover if the function that the oracle is computing is in this class or in this class. And let us suppose now that I have a quantum oracle. And the quantum oracle will compute the f of x in this way. Here I have x, here I have an ancillary system, and this will compute the value of x in this cat here, and here I have the y. This is the binary adjunction with this function. Let us suppose that I have this input state in this oracle. 0 plus 1 and 0 here, we'll have this kind of output state. And how to implement the oracle? We can implement the oracle performing CNOT gates and out rotations, right? But I don't know what is the operation of the oracle, okay? Other guy is doing this in the other lab. The guy will only send to me the result, and I can also choose what is the input. Okay, so we can consider the following situation here. Here we have the oracle, and here we have some input states. Here I have 0, here I have 1, here I have this Hadamard gate. Then when we apply the Hadamard gate to the initial state, we will have this state here after this unitary operation. At this point, we will apply this oracle evolution, which is also a unitary evolution to the system, and then we will end up with this kind of the state. If the function is constant, I have this first line. If the function is balanced, I have this second line. So we can see here that the state in the qubit A is different. Here I have 0 plus 1, here I have 0 minus 1, okay? Let us suppose that here I have a detector that will measure sigma z. Then I perform a Hadamard operation just to put the state in the basis of the detector. And then I have, if the function is constant, I have 0. if the function is balanced, I have 1 in this first line. So my final state is something like this. I have the binary addition between f0 and f1, and here I will have 0 if the function is balanced, is constant, and 1 if the function is balanced. So with just one measurement, just one execution of this algorithm using superposition plus interference, this is important. To get advantage in quantum computation, we need to explore interference. I can answer if this function is constant or balanced. So it was 1/2 of the operations that I have to perform in the classical way. We can get an even more advantage when we consider the generalized version of this problem. If you consider that the domain of the function is a any bit state, the image is still 1 bit, but the domain is a any bit state. The classical cost to discover if the function is constant or balanced is n is the number of bits that we have in the image. It's n over 2 plus 1. Okay? I will not perform this calculation because it's a bit longer. And in a quantum computer, I just need to call the oracle just 1 time. So, questions?
What was n there?
N is the number of bits. So I'm supposing that now my function of x has a domain which goes from 0 to 2 to n minus 1. So I have any bits, right? And the image is still 1 bit. So the n is the size of the input. So now x, for example, if I have 4 bits, x could be 0, will be in this interval, 0 and 15, right? And if I have 4 bits, for example, I need to call the oracle at least 3 times. In a quantum algorithm, I just have to call the oracle 1 time.
Okay, but if it comes 1 bit, then you have to call it 1.5 times?
No. This on I need to have more than 2 bits in order in order to have this scaling, right? Sorry? Yes. This was the first algorithm test in a quantum computer. This was tested in the 19th in a nuclear magnetic resonance system. And then this was also tested actually the generalized version was tested. This was also tested in trapped ions and many others setups. But the first test was in the nuclear magnetic resonance. So this was just to give you a taste about from where the quantum advantage comes from. So in general, we have to, in a quantum algorithm, we have to combine interference, non-locality, some kind of non-classical correlation, superposition. Entanglement is not necessary to get advantage. Maybe to get an exponential advantage, entanglement is necessary, but there are ways to get advantage without entanglement, right? At the beginning, people think about that entanglement was a necessary condition to get advantage. But now we know that it's possible to get some advantage without entanglement. And this is actually, as I commented before, the phase estimation algorithm. I will talk more about this algorithm when I talk about quantum metrology. But this is the general scheme of the Shor algorithm. The Shor algorithm is able to factoring a number in an efficient way. So this is an operation that involves implementation of a modular calculation. So the idea is to transform the problem of factoring a number in a problem of find a period of a function, which is the Euler function. I will not enter in details about this, how to do factoring, because we will need several lectures to present this in details. But what is important is, and this is what you call as the inverse of the fast Fourier transform, of a quantum fast Fourier transform. And then it's nice to find period. And the result that we get in the short algorithm is not a deterministic result like in the Deutsch algorithm. There are some possibility to measure something that does not able you to conclude what are the components of the product of the two prime numbers. And, but the probability to get the right result is quite high. If you repeat the algorithm few times, you can get the correct answer. If you get a wrong answer, you can test, because multiplication has a polynomial cost. So, and this is the number of digits. This is an illustration. This is the number of digits. This is the number of operations, elementary operations, number of gates that we have to perform approximately in classical factoring. This is in multiplication, and this is the quantum factoring, the short algorithm. So you can see that we have a huge difference. And this yellow shadow here means if we estimate the use of our best supercomputer in the factoring protocol, this is the limit of number of digits that we can do in the age of the universe, right? We have to run factorization during the age of the universe, right? So here we can see that a quantum computer, for a quantum computer, factoring is not much more difficult than multiplication. The quantum computers that we have now are not able to crack cryptographic codes because we have a lot of noise. For factoring, noise is a big problem.
Just a stupid question.
No, there's no.
What means 10 up to 9 in terms of time?
It depends on the clock of your processor,
Okay.
right? You can think about, okay, my processor can perform 1 trillion of logical operations per second.
Okay.
And then you can compare in this way.
Okay.
So, but anyway, this is the limit for a supercomputer in the age of the universe. So that's why cryptography in this way, using the factoring problem, is safe for our nowadays capability of computation. But for a quantum computing, this will not a safe way to do cryptography. So we need to introduce another cryptography. Nowadays, they talk about the number of bits when they convert the decimal number to a bit, and it's considered a secure communication. 2048 bits is secure, but 1024 bits is also used in a lot of commercial applications, maybe less. For example, in the internet, in our house, we use less, because the effort of an eavesdropper to crack your internet will not be so. But for a bank and for a government, it's necessary to use another pattern of security. So this is a taste about what is quantum communication. So this is the protocol known as super dense coding. This protocol can also be used or can be considered as a cryptographic communication protocol. and its knowledge also as one-time pad, quantum cryptography. So the idea is I have a source of entangled state. What is an entangled state? I showed to you that the C0 operation applied to a superposition state will produce an entangled state. So I'm supposing here, actually, this is the generation of the entangled state. I start with two qubits in the zero state, a Hadamard operation plus a C0 gate. And this will generate this state here. I cannot write this state as, let us suppose that I have the qubit A and the qubit B. I cannot write this state as a product of two state vectors, right? This is a sum of two products. I cannot describe anymore the state of one particle without describing the state of the other particle, in order to get the full description of the system, right? But I'll talk more about entanglement tomorrow, when I talk about quantum information in general, the quantum version of the channel theory of information. So the idea is have a kind of a source of entangled states. So I have a kind of telephone, of a landline. When I take this landline, it starts to come subparticles which are entangled with my partner in the communication. I have here Alice and Bob, the A and B guys in the communication. This is the usual setup in communication. So Alice will receive this quantum bit, this two-level system. This could be a photon, for example. And Alice will perform a unitary operation. And then Alice will choose between 4 possible unitary operations, and this will encode 4 bits. And Bob will measure this guy together with this guy, and Bob will find which operation Alice performed here. Then Bob can get 2 bits of information with just 1 traveling quantum bit. So in 1 quantum bit, we can encode 2 classical bits. That's why this is called as superdense code. Moreover, the operations that Alice will perform will be something like this. Alice will apply sigma y or sigma x, and this depends on I and j are the pair of bits that Alice wants to codify in this state. If here I have an eavesdropper, the eavesdropper will not have access to the information. So now I will introduce what we call the Bell basis. Why Bell basis? Due to the Bell's inequality, right? Because here we are using this non-local state, this entangled state. So this is the Bell basis that we call as phi. This phi plus, phi minus. This is the psi plus, psi minus. I can go from here to here, applying a sigma z operation, right? Or sigma x times sigma y, I can go from here to here, right? If I apply sigma x operation in this guy, in the qubit A, we will flip the qubit A, and we will get something similar to this, right? And so on. So we can measure this basis, this composite basis, using this circuit. So this circuit implements what we call POVM, or positive operation valued measurement. So I can measure this Hilbert space 4-dimensional using detectors that measure each qubit plus entangling operation, which is the C0 gate and the Hadamard gate, right? So if you evolve this general state here I'm writing this Bell basis in terms of x and y. This x and y means bit. I should use I and J without X and Y, in order to avoid confusion, but that's okay. When we perform the CNOT gate and the Hadamard gate, in the end of the day, we will have an output state like this. If the input state was plus, I will measure here 0. If the input state was phi, I will measure here 0. If the input state was psi, I will measure here 1. And so on in this other case here. And so if Bob do this kind of measurement, Bob will see which state was prepared by Alice, right? So Alice is only performing a unitary operation over 1 qubit. Then doing this, Alice can change the basis state, right? And Bob can get which state of the basis Alice is sending to him. And if an eavesdropper in the middle of the way try to listen the conversation, the eavesdropper, we suppose that the eavesdropper will only have access to the qubit A. So, are you familiar with the density operator? All of you? Some of you want that. I can talk about the density operator tomorrow. Just a few words, just 1 or 2 slides. Anyone want to see something about density operator tomorrow, or it's not necessary? Just one. Anyway, tomorrow I'll talk about a little bit. Okay, when we take, so all the information that eavesdropper will have access will be associated to the reduced density operator of the system A. So if we write the density operator of this integrated state and trace it over the variables of the system B, what we get is something which is proportional to identity white noise. So this is identity over 2. And we can have any phase here, right? The result will be the same. We can have any of the states of the Bell basis, the result will be the same. So for the eavesdropper, it's impossible to know what kind of operation Alice performed, because you need the another partner of the state. You need the particle B, right? So the idea is we have this source of integrated state, then Bob has a kind of a quantum memory to store the state of the particle B. Alice will perform some operation, then Alice will send 1 qubit, and then Bob will perform this joint measurement using this scheme here that I showed to you in the next slide, that this can be used to analyze the Bell basis. This is also what we use to perform quantum teleportation. So it's clear what is the source of security in this kind of protocol. The information is stored in a superposition state. This is stored in phase and also in the correlation of the 2 systems. So the eavesdropper only see noise, but Bob will have access to the whole information. This is the simplest quantum cryptography code. There are much more elaborated codes. So I'm going to finish my first lecture. So I commented very briefly that we can encode qubits in different systems. These are some of the examples. The systems that are going far in the commercial applications are the superconducting circuits and also trapped ions. So it's possible to trap 50, maybe 100, but the record is about 50, a little bit more than 50 ions in a linear trap. So these ions are inside of a quadratic potential. And then we have repulsion. People use calcium ions or terbium or rubidium. There are different kind of traps. And they use lasers in order to couple in a Raman scheme the ion with the motional degree of freedom. So here we have inside of the potential a kind of linear crystal, and then exploring some electronic transitions with two counter-propagating lasers, we can do things like we can produce Hamiltonians, effective Hamiltonians like this. We choose two hyperfine states of the ion, and then A here means the phonon of the vibrational degree of freedom, and sigma minus a dagger. Or we can also tune on the other sideband. We can also produce a Hamiltonian also like this, right? One is the blue sideband, the other one is the red sideband. And then we can couple the electronic degree of freedom with the vibrational degree of freedom. We can do it with this ion and with this ion, and then we can perform a CNOT gate between this guy and this guy. They use the vibrational degree of freedom as a quantum bus to make the different ions communicate between them. And this is, in a very, very short way, how people perform quantum computation with these guys. Here we have 7 ions. This picture was taken in Innsbruck, in the Heinerblatt lab. And this is a fluorescence of these ions, right? So in the electronic circuits, the idea is to use a superconducting ring like this, a squid. And then here we have one part of this string with geoelectric material, or we have some decreasing of the size in order to get a tunneling current here. That the current could be in the right direction or in the left direction, and then we can use this to encode 2 qubits. We can couple this guy to another transmission line, superconducting transmission line. So they use lithography over a chip in order to produce this kind of system. We can couple in a capacitive way, and then in the end of the day, we can quantize this Hamiltonian, and we can use this coupling with this transmission line in order to produce the gates between different qubits. The measurement system in this case is not easy to perform, but they can measure with a high fidelity. So it's quite important. In order to implement quantum computation, we need a control in the system that enable us to prepare an initial state. We have to control the interaction between the different qubits, and you have to be able to measure the qubits. So in each of the systems, we have different strategies to do it. And tomorrow, I will start talk about what is not beautiful in this thing, which is the coherence. So all of this quantum system is interacting with a kind of environment. And this interaction with the environment leads to the decoherency phenomena, and the quantum properties will decrease with the time. Then this will put limitations for the implementation of quantum computation, right? And this is my plan for tomorrow. And tomorrow I will also talk about a little bit of quantum metrology, and also quantum information, and also quantum thermodynamics. I will show to you in particular an implementation of quantum Maxwell daemon, and also how to use non-classical correlations in order to subvert the second law of thermodynamics, right? It's not we will challenge the second law of thermodynamics using these quantum devices, but we will not violate the second law of thermodynamics. We will just challenge, right? Thank you for your attention for today. And any other question? Oh, tomorrow I will also describe in more details this setup here, which is the setup that we have to perform quantum computation and test in quantum information using nuclear spins at room temperature. Sorry, it's not cold atoms. We have some molecules, but we have very cold spins. The spin, we can reach temperatures for the effective temperature for the spin system about nanokelvin. And I'll talk to you tomorrow about this. So thank you.
Question?
Are you familiar with Google's recent announcement of quantum supremacy?
Yes. Yes. I didn't talk about this because there is no paper yet. There is this idea about the quantum supremacy. So the idea of quantum supremacy is to show that a quantum computer can perform something that cannot be simulated in a classical computer. This is not necessarily something useful. Could be something random. And it seems that Google did it. And there are a lot of, all these companies, and there are several groups trying to find a way to prove that quantum supremacy. So it seems that what Google did was something like this. They have the qubits here in their superconducting processor. It seems that they used 50-something qubits. And they choose randomly some unitary operations between pair of qubits. And then they perform on another step, choosing again some random unitary configurations for these 2-qubit gates. In the end of the day, you can measure the system and you can see if your measurement is compatible with your expectations of quantum mechanics. But as I told you, also certify a quantum computation is also difficult, because if you want to perform a quantum state tomography, we have to perform an exponential number of measurements. And then with 50 qubits, quantum state tomography is almost impossible. So quantum state tomography is a way to reconstruct the state vector of the system or the density operator. In general, in the lab, we have density operators. We have something that's quite close to a pure state, but it's not pure. Okay, so then they did it in a statistical way, and then they compare with the predictions, with what will be the predictions of a supercomputer. And then the supercomputer will take a time much longer to simulate this random number of operations. So it seems that they did it. And what we know is the paper is submitted to a journal. This was performed by Google together with people that work on NASA. And some of the collaborators put the paper online, and then they take out the paper few hours later, but it was enough to some news media get the information, and it was announced in the Financial Times, etc. But there is no paper yet, so we have to read the paper to see. It seems that it's a long paper, and but this is one question. How, for example, IBM is offering quantum computation, right? How can I do to test if IBM is also doing quantum computation in the cloud, or if they are doing a kind of a simulation in a Rouge classical computer and saying to me, okay, we have a lot of noise. It was not noise. It was due to approximations in this classical simulation of the computation. So certification of a quantum computation is also an open question, and there are some protocols to certify if a quantum computer is really quantum or not. There are some people working on that also. Yes, it's a universal computer. They use an architecture quite similar to the architecture of IBM, based in these superconducting circuits. And they collaborate with the John Mattins from University of California in Santa Barbara. Actually, they hire the lab of the university to build the computer somehow. But there is also a competing computer with also 15 qubits of a company named IonQ in Maryland. The company belongs to one of the guys behind the company is the Christopher Monroe, a former student by David Wineland, the Nobel Prize. And they have much more accurate gates than the gates in ion traps, the gates that they have in circuit QED, circuit quantum electrodynamics. It's how we call these the superconducting circuits. And yeah, but we still in the limits that we call noise intermediate scale quantum technology. All these applications for quantum technology that involves many qubits are quite noisy, because when we increase the size of the system, the coherence increase. And there are a lot of people working in tasks that can be solved with these noise intermediated scale devices, but we expect that in 10 years or 15 or 20 years, these devices will be able to perform factoring, for example. But there are some proposals for useful tasks even in these noise machines, some optimization protocols, for example. And when we go to a small system, we can perform very high fidelity gates, but we cannot perform something very useful, right?
Would it enhance significantly the use of qubits instead of qubits, like in quantum cryptography or something like that?
Yeah, there are just a few protocols involving systems with dimensional bigger than 2, like there is this Qtrit, which is a 3-dimensional system. And I saw some progress on that associated to quantum games. People trying to do, because, okay, we are using 2-level system because we are doing a kind of adaptation of our classical model of computation where we use bits. But in quantum systems, sometimes we have more than 2 levels, right? We have an atom with different levels, etc. We can encode logical qubits in this higher dimensional system, but we can also maybe use this higher dimensional system to process information or to get some advantage. But there are just few protocols exploring this kind of feature. So this is an open avenue to get something new. Probably this is another direction.
So far, the game that you have used in quantum computers are in the number of the processing, the number of operations that we have to do. The game that we have using quantum computers is the number of the operations, or there is something else.
I did not got your question.
Because so if you use quantum operations, you can do the same with classical computers, but much more faster, right?
Yeah, the point is when we use a quantum system, we have something that we don't have in the classical probability theory. We have superposition, we have interference, we have a new way to compute probability, right? So in general, the advantage that we can get in metrology or in computation or in communication are associated with this interference and also the fact that we have now complex amplitudes, right? And I don't know if I get correctly your point. And then one point is how to compare this with the classical case. So we have to compare in a fair way. So one way to compare is like what I showed to you about the Shor algorithm. We can compare the number of operations, or in the case of the Deutsch algorithm, the number of the times that we have to call the oracle. And then in the quantum in the quantum scenario, you have to perform less operations, right? But we can also say that okay, to perform a classical gate using transistor is much cheaper than to perform a quantum gate, because I need a lot of control in my quantum system in order to perform a quantum gate. That's why Google has this kind of model. You will not buy a device to run a device by yourself. For example, this company, this D-Wave company, sells the device. You can buy the computer. It costs 10 millions. It comes with a helium dilution refrigerator and all the electronic stuff to control the things. And we will need few PhD guys, with PhD to operate the machine. Google is selling the access to the system, which is installed in different facilities of IBM, sorry. And I don't know if it was your question.
How can we compare why a quantum computer is better than a classical computer?
Yeah, one way to do it is comparing the number of operations. The other way to do it is this idea of this quantum supremacy. So I will perform a task in a quantum computer that will take few minutes or few seconds. In a classical computer, this will take years to be computed. So this is more or less the idea. Then it's clear that, okay, we have supremacy, but this idea of supremacy is not associated to something which is useful for something. When I talk about the algorithms, we was considering something that could be useful. Any other question?
So if the supremacy is not proved, maybe you could build a quantum computer and then realize that there's not quantum supremacy.
No, at principle, there was this paper that was put online, and then they take out. And at principle, there is a paper submitted by Google proving the quantum supremacy. But I didn't read the paper, unfortunately. I'm not the referee as well.
Okay. Thank you.
Thank you.
Very much. We meet again at 2 o'clock. There will be the group picture at the time of the coffee break this afternoon. And you might have received an email
Hey.
that at 8 o'clock,
Portuguese or English?
so far